Now that we've taken data and found the relationship between the force of gravity acting on an object and its mass, we can use that relationship to solve some problems. Going back to our lab, we found that as we increase the mass of an object, the weight of the object increases. Now, just a quick reminder that an object's weight is simply the amount of gravity acting on it. So the force of gravity is the same as the weight. Those two things are interchangeable. The line on our graph turned out to be linear, so that tells us that the relationship is linear. This means that the force of Earth's gravity pulling down on a mass increases with a constant rate as the mass increases. Now, the slope is defined as the gravitational constant, and it is abbreviated with a lowercase g. The accepted value of this constant on Earth is 9.8 newtons per kilogram. And wherever you go on Earth, this value is the same. So if you were to go downstairs and do this lab, you would get 9.8 newtons per kilogram as your slope. If you were to go to California and do this lab, you would get 9.8 newtons per kilogram as your slope. Now, this is not exactly true, now that we've said that. There are some places where this value will differ, but not by enough that we need to worry about it in here. Unless you're doing very, very precise calculations with the Earth, you don't need to worry about that. So for our purposes, when we use baby G in a problem, we will use 9.8 newtons per kilogram. So for every kilogram of mass, the Earth applies a force of 9.8 newtons. So since this graph is linear, we can derive an equation to describe the line. The y variable is the force of gravity, so we will substitute in weight for y. And x is the mass, so we will change x to m. The slope has a value and a label, so we will put 9.8 newtons per kilogram in for the slope. Since the y-intercept is essentially 0, we can ignore that and leave it out of our equation. So why can we do that? If you think about what the y-intercept represents, this is going to be the weight of an object when there is no mass. If you don't have any mass, you can't have gravity acting on it. Yet. We'll get into some situations where that gets weird. That gives us a basic equation of weight is equal to mass times g, where W is the weight for the force of gravity, M is the mass of the object in kilograms, and G is the gravitational constant in newtons per kilogram. Since weight is a force, then it will be labeled in newtons. Interestingly, while G is the same everywhere on Earth, it's not the same everywhere in the universe. On Earth, G is equal to 9.8 newtons per kilogram. What determines this value? The force of gravity is the force acting between two masses. If we are on Earth, one of those masses is the Earth. So the mass of the Earth gives us a constant pull of 9.8 newtons on every kilogram of mass. If we were to go to the moon, which has much less mass than the Earth, the gravitational pull would be less. So on the moon, if we were to do this same experiment, the slope of our graph would be 1.6 newtons per kilogram instead of 9.8 newtons per kilogram. So instead of pulling a kilogram down with a force of 9.8 newtons, the moon pulls down a force of 1.6 newtons. So let's check this out and see how that affects how we move.
We think so too. We were going to do a bunch of exercise that we had made up as the Lunar Olympics. Show you what a guy could do on the moon with a backpack on. But for a 380-pound guy, that's pretty good. They threw that out. Yeah, jump flat-footed, straight in the air. 300, about 4 feet. Wow. Charlie, that ain't any fun, is it? That ain't very smart. Well,
we have a few minutes left, so we decide to do the Moon Olympics. I decide to try to set the high jump record on the moon. And as I start to do that,
About 4 feet.
I bounce a couple of times, and then I fall over backwards. And as I fall over backwards, fear strikes. If I split my suit open, I'm dead. As John helps me up, I get very, very quiet as I listen to the pumps and the oxygen flow in the suit. Fortunately, the suit holds and my fear subsides.
So that video is always fun to watch because you get to see these grown men playing Lunar Olympics. And you can see why they cut that out. That wasn't something that NASA probably wanted them to do. So that really kind of shows, what happens if you're in lower gravity, right? So if the moon is pulling you down with so much less force than the Earth is, you can jump a lot higher. Jupiter, on the other hand, has a lot more mass than the Earth. The amount of gravity pulling on 1 kilogram of mass on Jupiter would be 24.5 newtons. Then there's the sun. If you could stand on the surface of the sun, every kilogram of your mass would have 274 newtons pulling down on it. So let's take our textbook to all these places and see what kind of forces are acting on that. So our textbook has a mass of 4.4 pounds, and we would want to know what is its weight on Earth, on the moon, and on Jupiter. So how do we find weight? It is the force of gravity pulling on a mass, and we need to take the mass times g for whatever place we are on. We have a little problem though, because mass here, mass is measured in kilograms, but we are given pounds. So do you remember how to convert from pounds to kilograms? Remember there are 0.45 kilograms in every pound. So 2.2 pounds times 0.45 kilograms will give us a mass of 1.98 kilograms. So now we can use our equation. So that is something really important to keep in mind. Whenever we are using these equations with a constant, so G is a constant given in newtons per kilogram. You can't multiply it by pounds. You have to multiply it by kilograms. On Earth, G is 9.8 newtons per kilogram. So we're going to take 9.8 times 1.98, and this is going to give us a weight of 19.4 newtons. So do you think that seems reasonable? Remember, we have an example of 1 Newton being pretty close to 1 apple. Go pick up a textbook. If you were to drop that on your head, would it feel the same as about 20 apples dropping on your head? Don't test that, just hold it up. Now, what about the moon? G for the moon is 1.6 newtons per kilogram instead of 9.8. So how does this change our problem? We're going to multiply 1.98 times moon's gravitational constant, which is 1.6 newtons per kilogram. And we get a weight of 3.17 newtons. Think about how different that number is compared to the Earth. Instead of 20 apples, we have 3. It is kind of fascinating when you think about it. And it kind of goes back to the astronauts jumping on the moon. It's a lot easier to take your mass and lift it up. What about Jupiter? It has a G of 24.8 newtons per kilogram. So what does that do to our weight? We take that 1.98 kilograms, multiply it by 24.8, we're going to have 49.1 newtons. That's a lot of apples. All right, now pause the video and see if you can determine the weight of a 25 kilogram object on the surface of the Earth. So this is where we start getting into story problems. And the first thing that we really want to do is think about, what do we already know from our problem? We know that we have a mass of 25 kilograms, and that's really all the problem gives us. And we're trying to find the weight. So how do you find weight? Weight is equal to the mass times the gravitational constant of whatever body we're on. It says we're on the Earth, so even though the problem doesn't give us that number, we know that G on the Earth is 9.8 newtons per kilogram. So now we have m and now we have g. And so we can take that and we can plug it into our equation. So 25 kilograms times 9.8 newtons per kilogram is going to give us 250 newtons. Now this one rounds out pretty nice, right? We have 3 significant figures with our 25 kilograms, and we have 9.8 as our constant. So we can round this to 250. Pause for a second. See if you can solve this one. So this problem is the same, except that we are trying to find the weight of our 25 kilogram object on Jupiter. So we were given the mass. And again, to find the weight, we need to know the mass and the gravitational constant. So since we're on Jupiter, we can go look that up. It was 24.8 newtons per kilogram. So we're going to set this up the same way. We're going to take our mass of 25 kilograms and we're going to multiply it by 24.8 newtons per kilogram. And we're going to get 620 newtons.